based on particle physics. Dr. Satyanarayana has published about 300 research papers and proceedings in national and international journals and conferences. His very first paper won the Best Paper Award by Institution of Electronics and Telecommunication Engineers (IET). He guided a large number of doctoral, master, undergraduate students. He was honored with the Homi Bhabha Award in Science Education. Dr. Satyanarayana is a fellow of Institution of Electronics and Telecommunication Engineers as well as Institute of Engineers (IE). He is life member of and has served on the governing council, the Instrument Society of India, as well as a member of Indian Physics Association. He is senior member of the IEEE and is currently the immediate past chair of its Bombay section. He has previously served as the secretary chair of Signal Processing Society as well as the chair of technical and professional activities of the section. He has also served as an executive committee member as well as the vice chair technical activities of the IEEE India Council. He won IEEE Bombay Section Outstanding Volunteer Award for 2014 and IEEE Headquarters MGA Achievement Award for 2016. Warm welcome to Dr. B. Satyanarayana. I request Sir to share his views on the topic of today's session, that is scientific conduct. Thank you,
Welcome,
sir.
sir. Thank you.
Thank you. Thank you, Dr. Haladankar, and also sincere thanks to Dr. Y.S. Rao, who invited me to share some of my thoughts on this particular a topic which is of very close to my heart. Not just because I'm involved in the research activities at TIFR, but also because nowadays the ecosystem for research in the academic institutions is also on the rise, thanks to the general overall climate, I can say, in the country, and also general importance that everyone, all the stakeholders, in the sense the institutions, the faculties involved, even the students who are the end beneficiaries, all of them realize that this is where an academic institution also must progress to, and this is how an academician also must progress to. So that is why I think it is a very important topic. So let me see if I can share some of my thoughts on it. Of course, it is possible that some of them are biased as I come from a particular community, but I think most of these what I kind of try to share today will be applicable equally well for communities coming from academic world as well. So with those introductory comments, let me start my presentation. I want to share the screen. Can you once again confirm that you can see my slides?
Yes, sir. We can see.
Okay, excellent. So if you find any time the screen is having some trouble or audio, etc., please feel free to let me know. Right. Okay. So I was asked to sort of speak on a specific topic, which is the conduct of scientific work or scientific research. So that is a very broad, of course, general topic, under which I saw that there were several topics that were enlisted below. So I'll try to keep my presentation to as many, as much as possible to within these topics. So one is talking about ethics with respect to the basic science and research. Today's presentation, except for maybe first one or two slides, I try to assume that the science or engineering or technology, etc., they're all same, but essentially working towards the research in those fields. The most important attribute to a researcher, of course, is intellectual honesty and also the integrity that one must maintain, because most of the time when a researcher communicates to the public at large or the peers at large, one goes by an assumption that the researcher is actually reporting what was observed, what was calculated, what was analyzed, and what was concluded. So many times, irrespective of the fact that one is supplementing or providing the necessary plots or necessary analysis, necessary calculations, but there is no means to know absolutely without any doubt that what is being presented is, from the data or from the paper, that whether one is honest or not, right? So therefore, to large extent, the general peers or the other community largely depends on the fact that the researcher is, possess highest level of honesty and integrity. To some extent, that goes without saying, because when you are doing a research, this is something least that one expects. The other thing is, when you talk about so-called misconducts, then there could be quite a few of those attributes, sometimes giving false evidence of what is not observed, or sometimes maybe you didn't observe, but you try to kind of fabricate certain results or conclusions to meet your, let us say, what you initially enunciated, in some sense, the hypothesis. And of course, the worst, I'm sure this aspect would also be probably covered by other speakers in this event or in this program, namely the plagiarism, which is considered of late quite on the increasing scale, and so therefore everybody is generally concerned about it. We'll talk a little bit about it, but generally saying that you sort of in some way steal the information or the description or the wordings or the figures or the plots or whatever it is, which belong to the studies done by someone else, broadly speaking. Then there is also a similar, in some sense, misconduct, where you kind of try to increase maybe the number of publications due to either peer pressure or due to whatever the reasons is, trying to kind of make something like a duplicate publication. So the same material you publish in more than one journal and call that as a different publications, or in some sense, the material of one publication has been, overlapping with the other material that you already published. Of course, if you're working in a particular area, there is certain amount of overlapping definitely is assumed. You cannot completely write papers which are disjoint from one to another. Normally, a researcher starts or ends one's life not working in so many fields, maybe 2 or 3 fields in one lifetime. So therefore, there will be certain overlapping, but if the overlapping becomes too large or very intentional, the problem really comes up. This is sometimes, there is also something closely related field of what you call salami slicing. So you kind of, again, intentionally kind of divide the material into, so that they make multiple publications and increase your publication count, rather than putting all the material that is relevant to a particular conclusion in one paper. Okay. Also, sometimes you did certain studies, right? You did certain studies, you found certain data, certain results, and so on. But you chose to report only some parts which somehow seems to be something matching to your hypothesis. It is like saying that, I took some readings, but some of the readings happen to be falling outside what I think should be the fit. So therefore, I remove those points and plot the rest of the points. It's something like that. Okay. And sometimes the worst part, of course, is completely misrepresent and then draw conclusions which have nothing to do with the data that you observe. Now, these are just a kind of skeletal definitions or skeletal meanings of what various topics that are under this. So obviously, we'll go and try to elaborate a little bit of each of those. And as I said, some of the examples which I'm more familiar with, I'll try to sort of give them as case studies. But please feel free to kind of interrupt me or ask me questions at the end on any of these topics. I'll try to kind of answer them. Okay, so I want to spend a few minutes at least on giving generally my thoughts about the science and the research that encompasses not necessarily, as I said, science, but also all other fields. Normally, when you do either science or, for that matter, you can also replace science by research here. we talk about a kind of investigation, right? But the investigation should be around a particular, reasoning. It's not that randomly you investigate certain things. And most of the time you want to do this because you want to study some phenomena. For example, many of us do, Sir mentioned about high energy physics and so on. So we kind of look at what the natural phenomena of certain particles that are inside the matter, but at a very, very deep level. And why do we do this? We do that because we want to discover some new principles which didn't exist before or improve upon if those principles already exist. And you also want to gain, of course, more knowledge, let's say, on some of the natural phenomena. I keep saying natural, etc. It's just because I happen to work with natural sciences. Now, if another person coming from biological sciences or, living organisms, or for example, or any other field might want to say you want to study on the biological phenomena, etc. Also, to this audience, I guess I don't have to stress much that whatever we do in science, many times when you want to express, when you want to communicate, we always end up writing all that, complex, not complex, but the long, verbose kind of material using simple equations, right? We are all familiar with that. So maybe it is fair to say that mathematics is in some way a mother tongue of science because you speak science in mathematics. So some of the people, like even maybe in the audience or elsewhere, once the science is kind of perfected, at least in that particular domain, they try to kind of look at it and see how you can convert that into a practical application. So you take science and then, look at, let us say, produce some technology which is useful to the mankind. So this particular skill or technique or knowledge of manipulating of the nature for human purpose is the job of technologists, and obviously they do some of the most useful work to their humanity in some sense. Engineers try to kind of pick up the technical know-how that was produced and then try to optimize use of, let us say, various resources. Could be power, could be cost, could be weight, could be volume, could be many things of this product. And ultimately, if you want this particular technology to reach to the person on the street, you would like to kind of optimize sometimes cost, sometimes maybe volume or weight, or sometimes money. So I think it is fair to say that scientist studies nature, technologist manipulates nature, and engineer actually exploits the technology for human purpose. So most of the time we stop as scientists just knowing about it, and once we know, we don't go further. But engineer actually want to build things by his or her hands. So in some way, I normally have this favorite way of saying technology, science, and engineering are three surfaces of the same coin. Many times we also talk about branches of engineering, and we all know as researchers, all these branches of engineering has quite strong roots of science. You can take any branch of engineering and you will actually end up talking about the science that the forefathers have done it, 100 years ago or 50, 60 years ago, and so on and so forth. So yeah, we all, of course, are born scientists because we used to ask questions when we were young. But sometimes in the school, maybe depending on the teacher who taught us science or social or mathematics, either we love a subject and we decide to do research or maybe further studies on that subject, or sometimes we get scared and try to kind of leave it at the earliest opportunity. So in some way, without causing any disrespect to any of the teachers in the school level, but sometimes I think good or bad, it really comes down to who taught us the basic subjects at the school level. So once you kind of want to, get scared or move out of the research or science, then we kind of want to do, let us say, what is safest to be an employee rather than, have this bent off mind of research. But what is worst sometimes, as you agree with me, I hope, is also we try to kind of force upon the same kind of nature of thinking to our children sometimes. I said this last sentence because even our founding father of our institute, whom you all know, Homi Baba, he couldn't escape because his father wanted him to do mechanical engineering. You can see the letter that he wrote to his father, which I reproduced on the right side. And he really argues with his father, saying, I'm sorry, I don't know engineering, I can't do things much in engineering, but my love is physics, and I know that I can do great things in physics. So please allow me to do physics. I think it's not surprising that Baba's father wanted him to do mechanical engineering because, as you know, Homi Baba comes with Tata's family, right? So maybe he wanted him to head one of the Tata empires rather than going and doing research. But in spite of all his pleading, his father didn't agree. Finally, he told that, okay, go and do mechanical engineering, and then I'll allow you to do science and so on. And Baba had to do that. So, of course, this is just in a passing. But coming to more closer to where we all live and work, I think research is not just confined to only where some of us set up huge experiments to do what we do in high energy physics. But maybe life sciences people will do something else in the labs and chemistry and so on and so forth. But academics, like most of you who are on the call today, you actually end up teaching logic, teaching how to arrive at certain conclusions based on what you know beforehand. So in some sense, this is the whole research is about reasoning, right? The only thing that if at all one wants to comment about the comparison between these two is that unlike research where you build dedicated experiments involving billions of dollars, you might really have the experimental parts only are limited to maybe teaching labs or some limited scale of research labs in your academic institutions. Similarly, even there is no dearth of research in the industry. Sometimes you tend to call them as applied research, but the biggest part, probably benefit or advantage of industry is they have huge resources, raw materials, money maybe in some sense. They are consultancies and services. They do have plenty of those opportunities. But my hunch, or you can say my take on this is research can equally excel in not necessarily only in research institutes, but universities where you have huge resources in terms of students, and as well as industries where a lot of equipment and material are available to specific resources that I'm kind of talking about. I will actually now try to skip some of these parts, but I just want to give an overall gist of things to say why research in education institutions become very, very important, because in some sense, what you do without you probably noticing very deeply is that your job actually involves in understanding the research process and how the science grows or technology grows. You also teach your kids like how assertions require supporting evidence, because you teach in the classroom, and when you take them into the teaching lab, you tell them, look, what I told you as a theory, now you are going to kind of look at the supporting evidence and so on. You integrate theory and practice that, and you also understand how the knowledge is constructed brick by brick, and teach a lot of lab techniques, etc. Ability to analyze data, develop skills to interpret the data that their result, they got it and so on. And of course, in that process, you also yourself as well as your kids, your students, try to work independently. And many times we also notice that many times the experiments do not take us to the results that we expect. So the obstacles and failures are very, very common. So the point I wanted to say is either the university or institution, whichever wherever you are attached to, they will also benefit from when you actually work and do a research work on the campus in terms of publications or patents, and also increase its like let's say institutional visibility in the scientific community as a whole. After all, these days, all one talks about branding, ratings, rankings, etc. These are the main attributes for getting enough funding and so on. So I want to end this part by saying there's a lot more, I think, responsibility of the management in some sense. The institutions must really develop research which is conducive atmosphere on the campuses, not just only of course, innovation cells nowadays, incubators have become commonplace in every institution, but that's only like feeding, let us say, our interested young students, but one also must make sure the faculties as well are benefited by setting up and maintaining some kind of research labs besides teaching labs, and obviously, certain financial assistance and making them to also connect up with the other peers across through professional memberships becomes a major part of this. Okay. So I'm not saying something in hello. I mean, you know better than me. Nowadays, all these rankings that one is talking about, there is a huge fraction of the ratings that come is actually coming from research and professional practices. Here, what I'm kind of trying to show is the professional, the so-called research and professional part of the weightage of marks that you see for NIR ranking. We're almost talking about 30% of it, which comes from combined, metric like publications or quality of publications, the IPR that you generate to yourself and to your institution, and the patents and huge projects that you brought on the campus, which are very, very impactful to the society and the technology at large. So it's not without evidence that I'm saying that um, the research conducive atmosphere is what is kind of going to bring about a huge benefit. Yeah, again, I just want to say this in the passing. When I said sometime back, the country and the whole of society ecosystem is very conducive right now. I really meant also by saying that the NEP 2020 also lays huge stress on research, atmosphere research, based learning on the campuses, and which I know all of you started getting on. In fact, I think you are already following maybe from last semester or at least this year onwards. So which means that now you are no more talking about the degrees that come with just academic classroom or lab teaching only, but actually the students will have a peek at even the research that goes on the campus through your eyes, over your shoulders. So which means that you as a faculty are going to be torchbearers for looking at taking the students in more convergent with the research atmosphere. So depending on how the student performs, hierarchically, one is kind of trying to talk about whether one gets, like whatever, in the diplomas and degrees and, master programs and, whatnot. So, but what the point one is talking about here is the education so far, the degrees so far, which have been largely confined to it's a one-way kind of a teaching and learning and putting up on the question on the exam and passing out and going and looking and trying to explore something totally unknown to them. Now we want to kind of engage with the exercise with the students, not just only the classroom teaching, but also giving a flair of the world beyond that, namely able to kind of innovate, able to kind of research, able to kind of bring something original out of their liking or thinking, right? But that's a new dimension, but that is, I think, a very, very important dimension if you really want to make a better meaning of our students, and more importantly, also making them more in quote unquote employable, in the sense that a student who is better equipped with able to reason out, able to understand, able to solve problems, able to kind of find a reason to bring a new kind of value out of the existing one, is somebody who can actually be more useful to an organization as an employee, rather than a person who only knows how to write a few tens of lines of code or put on or put off a switch or something like that. So I think we are empowering them. We are better empowering them. Okay, we are better empowering them, but through our empowerment in terms of going into doing a better quality. I say better quality research than that has been there earlier. Of course, when you talk about doing research, we are all very excited as young people, but we want to kind of do lots of things. But in reality, of course, this is just for joke. I mean, don't take this very seriously. But I really wanted to kind of say, this is a cartoon I picked up from somewhere. It kind of, there are also a lot of constraints, both in terms of money, in terms of time that we have. So we have to toggle between classroom teaching and going to lab and doing research. Sometimes funding is a big issue. Sometimes management is a big issue, and so on and so forth. Yeah, you might have a very noble ideas to do front-ranking research, but you also have to ensure that all these hurdles are crossed before you can publish papers and get name and fame. So therefore, since I said in the beginning very openly, in some sense, said that research can be done equally well in industries and academic institutions, not necessarily only for research institutes. But I think it is fair to kind of say that, well, I mean, all the problems are of not same nature, right? If you look at the graph or the picture on the left, you will actually see that one is talking about a kind of a scatter plot in which there are problems which are very hard. Uh, there are problems which are somewhat easy. There are problems which are, they give on the y-axis, which will give you a very small gain in knowledge. Maybe you don't get a Nobel Prize, maybe. But there are also some problems which are like, they give you a large gain. Maybe a paper that gets published in a very, very high impact journal, for example. Okay. Now, obviously, you will tell me that what kind of problems you will like in this 4 sort of quadrant. You will say, I would like to do a easy job and get a large gain or something like that, right? Which is which we all want to aim at this. Okay. But that doesn't happen. Quite often it happens. Many of the problems with the current research could be of easy, but they may not be very interesting, which is small gain, right? Okay, but we call them loosely as low-hanging fruit, right? Which means that we don't make much effort to get the fruits in our hands. Okay, but on the other hand, if you look at problems which are typically solved by research institutes, they are unfortunately they are quite hard. But sometimes could be of also have a low kind of interest, because many of them we find that no, it is very hard to attempt to solve these problems and so on. Okay, I mean, some problems they give a huge challenge. I mean, if you are able to solve them, you'll get a great, as I said, benefit. But it also requires very thorough understanding. So all these 4 combinations, let it be there, it doesn't matter. But what we would like to do, if we are sitting in an academic institution, and I would like to kind of pick up a kind of quadrant of problems which are suitable for me, I will actually go ahead and say, okay, it doesn't matter. My small gain is okay, because as I said, my idea is that I want my students to look over my shoulders and understand what is the research culture in some sense. It's all right if you publish in a small journal. Okay, so let us take up problems which my students, masters, or maybe even undergrads can join me. Okay, now if I'm able to kind of become a little convergent or better or something, yes, I will actually try to go and look at, maybe there are some postdocs in my department or some other junior faculty who can join me in getting on to doing something bigger problems. Maybe when I become myself a senior professor and able to kind of gain knowledge as well as certain influence, I can say, in the organization, I will go and kind of attempt problems which are maybe hard, but doesn't matter. Now I'll get a larger gain in the outlook, right? So therefore, I think it is fair for me to kind of start with this quadrant, go to this one, and maybe see if I can kind of reach out. Okay, so this is I think what one must kind of limit your understanding and what kind of problems to be taken. Now, therefore, well, I mean, that is a little bit of philosophy in some sense, but when you come down to actually taking up a field of the research that is suitable to you, obviously you want to choose something which you know. You don't choose, if you're a communication person, you won't choose a field in physics or or biology or whatever it is. And you obviously also choose topics which you really love. It's not just for teaching a course or something, but it's something which you want to kind of take further. But unfortunately, or so, what is also important is this alone is not enough. You also want topics which are of concern, which are of importance to the current audience, namely the stakeholders. Even if you love certain topic, if that is not what the people want it on the ground, maybe you will not be very popular researcher. Maybe your project itself will not be funded because you are talking about some string theory or something which maybe you can't convince people that it is going to be useful. But if you are doing research on something COVID-related thing in the year 2000 or 2001, 2002 or some, I mean, there maybe the chance is that you will get a funding because that is something where, of the current topic. So therefore, in some sense, I think the topics that are better chosen are the ones which are sort of, to say in your language, union of these three sets. Okay, but also you would like also be known, very popular, right? In your community, you also want to say so and so is an expert in cloud computing, so and so is a dada in autonomous robots, etc., etc. So therefore, one might want to kind of have a look at certain literature. What I saw on the left, if you look at the so-called IEEE Explore, which is one of the repository of IEEE, where millions of documents, papers exist. If you really look at and ask, okay, say, give me kind of technologies that are right of fueling the fourth industrial revolution. So it is likely that you will get such kind of figure, and you can actually make out by the number of documents or by the number of papers that are reposited on the Explore, then maybe you can say that, okay, so that means Internet of Things is great, or big data is great, or autonomous robots are great. But maybe 3D printing, so okay, I don't think it is very popular as of now, or whatever, right? I mean, you can guess, you can get an index of how these things are sort of going on, and what is best selling in the market. I mean, what are the best topics that you can get your publication well, and maybe you get funding well, right? These are important things. Now, let me get on to go a little deeper and take two lines of problems. One is something to do with, let us say, simulations. I also thought that I will give a flavor of mathematical modeling, but I refrained from doing it from want of time. And then I'll also try to kind of give some, measurements, experiments. Okay, so one is of simulations which you do before you go down to kind of set up an experiment. And the other one is the experiment itself, and how are you going to mitigate the measurements and the errors and so on and so forth, right? So we all do sometime or the other the simulations, right? These are essentially, we are talking about a class of algorithms. Of course, we use computer, obviously. But the most important thing, as you would see very soon, is that in the simulations, we actually look at the heart of, or the beginning, the main seed of the simulations is how you can kind of get a sample which is a random number, which is within the space of your problem, right? Whatever problem you take. So it looks very interesting to know. So you use randomness to solve problems which are actually deterministic in principle. So it looks somewhat weird that one can solve a deterministic problem by taking a randomness, but you will see soon that is how one works about it. And in most of the physical problems, right, we only resort to this if we find it is impossible by other approaches. For example, if you have a problem which you can very well, mathematically deduce, then there is no need for simulations. I mean, you can calculate and say, this is my value. I mean, it's a very deterministic kind of calculation. I don't need simulation. But if you can't do it, but this is the one way of resorting to. So it may be used to solve, in principle, any problem, but I should know beforehand what is the probabilistic interpretation or probabilistic distribution of the entire search space that I'm talking about. Now, the basis of this, or the assumption, or the basic principle is that what is called law of large numbers. I'm sure many of you are aware of it. So the integrals which are, let us say, described by what is the value that I expect, right, of some random variable. Suppose I can take whatever random variable. Now I can approximate this by taking simple mean or ordinary arithmetic mean of individual or independent samples of that variable. So I'm actually dividing the entire search space into a small sample space, and I'm actually asking for simple mean which is of a simple mean of random variable. So I'm actually doing something like a divide and conquer. Okay. So just to quickly, this is a typical Wikipedia kind of an example. Suppose I take simple dice, and I kind of toss it. If suppose it has a 6 faces, and if you do enough number of flips, I can ask you what is the expected value of the average value, right? Average value, not a single sample, we will quickly say it is 3.5, 3.5, because all are equally probable, then there are 6 phases and so on. So same way, if I have large number of such 6-sided dice rolled, large number, very, very large number, we'll see how much large number. Then the average value of their values, which we said sometime back as simple mean, that will converge on. That will converge on to the value that you calculated with a precision which is actually increasing with the number of dice that you roll, number of samples that you do. Okay. So this particular probability you can call as empirical probability of success in a series of Bernoulli trials, right? Which will convert to the understanding of the theoretical probability that we saw in the previous slide. So suppose I take these dice and now start actually doing an experiment. I know that theoretical mean of this particular experiment is 3.5, which I have drawn a blue line, and then I started kind of doing sorry, a large number of samples. The samples are on the x-axis, the average value is on the y-axis. You can really see that in the initial stage, the value really oscillate around the mean value, which is nowhere near. For example, you can see initially up to a few hundred samples, it doesn't converge on. And as you go, maybe a few hundred samples, that the law of large numbers comes into play, and you will be able to kind of converge on. Remember, when you started, you didn't kind of start with any particular specific number. It is a random sample. You randomly tossed the dice, right? So, in fact, it is very interesting, and I'm sure many of you must have seen recent movie of Oppenheimer. So, the entire 1940s, bomb project of United States was actually kind of in a way started with this simulations project. Some of you must have heard the name Enrico Fermi, an Italian scientist. He actually the one who actually started looking at, because when you do a bomb explode, you see large flux of neutrons coming up, and he wanted to really study how do the radiation is going to kind of affect when the bomb is exploded, for example. So this in 40s, as I said, Stanislav Ulam is the guy who actually picked up from Fermi's theory, and he was actually working on the weapons project as Los Alamos lab. Many of you know John Newman, who actually built the so-called ENIAC, the computer to carry out these particular simulations. So from 1946, investigating various shielding that are required for let us say the radioactive material and the distance that the neutrons would likely to travel, and all those studies at Los Alamos lab were actually studied. They couldn't, of course, solve them using, as I said, conventional or deterministic mathematical methods. This is what I said. If those methods fail, then you really have to depend on this kind of algorithms. Since at that time everything was a secret project, as you would have seen in that movie, so people don't want to kind of say what they're working on, and they kind of wanted to call these simulations as Monte Carlo. Monte Carlo happened to be a casino in a country, Monaco. So they somehow named. I think you also remember each of these people, and many of the things were nicknamed, and that is how they were communicating, so that their enemies won't know what they're talking about. So therefore, the simulations are in some sense central to the so-called Manhattan Project, which is 1945, as you know, during the World War. So let me skip this. So to just give you, again, a simple Wikipedia kind of example, suppose if I want to say what is Monte Carlo, what do you mean by saying take a random sample and get a deterministic value, right? Suppose we say, we want to start by saying that I want to take a quadrant, a quadrant which is inscribed inside a square. So quadrant of a circle, you can see 1/4 of a circle, which is inscribed in a square of a unit length, unit side, you can say, right? 1 and 1 here. And so therefore the radius of the circle would be also unit 1. Okay. And we know that this area of the ratio of the areas, okay, because this is pi r square, you're only talking about 1/4 of it. So pi by pi r square by 4, right? And whereas this one is a square, because that is the area of the square. Now the ratio of these two will be obviously pi by 4. Okay. So which means if I get that the ratio of these two, then I simply multiply that by 4, then I get the value of pi. Of course, we know in this case what is value of pi, right? Very accurately to the to whatever decimal place that you want. But I'm just giving you, demonstrating you as a kind of example. So what you do, you draw a square like in your program, and inscribe a quadrant in this, okay? And now you start, placing a random variable, a random number, as you produce a random number and plot it in this, okay? Of course, if the random number happen to be outside this, you won't plot it, obviously. But as long as it is within the square, you plot them. Now, after you've done all that, because it is a software exercise, you count all the number of points which are inside the quadrant, okay? And also you say what is the distance from the origin is less than 1. But why it's less than 1? Because this is the circle, which is a quadrant of that is what is drawn. Now, the ratio of the total number of points that you count from the inside count and the total count is the one which you will get pi by 4. Okay, multiply that by 4 and you will get the value of pi. Now, okay, that looks very stupid and a simple example, but what I wanted to kind of demonstrate to you is that if you see the n, which are number of samples here, and the value of pi, which is the value that you're really wanted to see, you can really see starting from very small number of samples to very large number of samples here. And you can also look at the value of pi. Obviously, as we said, law of large numbers, you are able to kind of prove that you need larger and larger statistics in order to get a more accurate value converging onto the average value that we demonstrated in the previous one. In principle, any problem that is not a deterministic problem you want to tackle, it is possible to solve them by such kind of exercises. And it is not only for people who are working in physics or science or something. The work, there are Monte Carlo simulations are used, for example, in engineering sciences. For example, what happens when, let us say, if you are a VLSI manufacturing company and you produce millions of chips every day, and you are supposed to kind of give a data sheet to about the chip, all values, parameters, giving what is the minimum value, maximum value, typical value, and so on. Do you think that you go and power up each of these ICs and measure the values and give you? No, you don't, right? You actually take essentially Monte Carlo simulations of these parameters and then look at how much variation that is going to kind of happen. Of course, you do some batch production quality control, but those you want to only see that those numbers actually fall within the calculations that you have done by simulation. Similarly, you could also talk about a lot of other applications these days coming up. Pure, even engineering, like you can say civil or mechanical or other subject, before they build such massive structures that you see around, every one of these structures go through simulations, and only based on the results, then you go ahead and do the actual engineering design and so on and so forth. So it has become a major force where people are able to kind of get good, not only good employment, but also getting a very, very high impactful research out of it. Now, if you have done some simulations and you want to go ahead and actually build an experiment or a research project, you kind of talk about delimiting your research problem per se, right? Everything on the world you cannot solve. So you kind of delimit your problem and you go ahead and actually solve about what is the research objective that I'm going to look at it. Obviously, a lot of work has already been done by your peers, so you don't want to repeat the whole thing. You go ahead and actually read all that has been already done, so that you can better define your research objectives above. Okay, and that is how finally, as I said, you delimit the research problem, not from where you started, but this is the problem which is now the contours of which are better defined because you had read through the literature. Based on that, you say that I'm going to kind of do this, and if I get this result, this is what my hypothesis is. So based on the hypothesis, I kind of look at the variables. What are the variables which I'm going to actually measure from the real experiment before I go ahead and design the research problem or research instrument and build the whole stuff there, right? It can be very simple tabletop experiment. It could be a huge experiment like some of us do, which will take 20, 30 years to actually design and build. But Doesn't matter. The scale is different, but the methodology remains something very similar. And I also, in the process, designed some of the tools which are required to get the data from the detector, and also design the tools, software tools, to also analyze the data. And you'll be surprised to find these days, because of the fact that people want to do actual very extensive simulations before setting up these experiments, the data analysis tools are already prepared beforehand, because you need them to analyze the data which is produced by the simulations. And the same software tools are also becoming useful when you actually get the real data from the experiment. It's very, very interesting development that happens. Of course, once your experiment is ready, you are going to collect data, you are going to do processing, you are going to analyze this data, and then the real stuff comes here, because you want to look at the data and interpret what it means vis-a-vis what you actually said in the beginning of your hypothesis, right? Um, of course, then you kind of draw conclusions and so on and so forth. And many times you want to, of course, write a research report, but more important than that is you want to report to your findings as early as possible to the community by way of papers, right? So this is the overall scheme of things. It doesn't matter whether, as I said, it's a simple problem or complicated problem. But of course, the flowchart on the right exactly says the same thing. The only thing is, it's like, I mean, when you analyze, when you draw conclusions the way I said here, it's likely that what hypothesis that you have drawn was actually true. You must be very happy in that case. You go ahead and sort of report the results, but sometimes there could be an issue, and most probably there could be an issue. Then you'll go back and try to kind of make changes in the hypothesis, make changes in the experiment, make changes in the data. Therefore, data will be different, and then you kind of repeat. And I think, however, one point we all must remember is when you say that data is not matching with hypothesis, not every time it is something to do with you did a bad experiment or a bad hypothesis. It could also mean that you are actually on the verge of discovering something which didn't exist in the world, right? It's quite possible that you hit upon something which something totally new, which nobody had ever kind of went and analyzed or went and sort of did experiments about. So when such thing happens, you don't have to start feeling frustrated or start blaming you. It is also possible that it is opening a new window, maybe to a new science or engineering. So one must remember these kind of things. Now, unfortunately, unlike what I told you about the simulations, when you actually set up an experiment and typically use various elements to collect data, most common elements, of course, is maybe sensors, or you also kind of build certain electronics around it to collect the data. Maybe you signal process them, and how the whole chain of things. Sometimes you people call that as IoT. If there are large number of such devices sitting in the field and collecting data synchronously, and which in some sense brings collective evidence about certain hypothesis, right? Now that itself can be a big problem, because sensors themselves can come out, and there are lot of you can say attributes which are difficult to control and understand fully, right? So, for example, the signal that it is producing, the duration of that signal could be depending on physical process, sometimes maybe a signal production process in the external circuit. You may have many times the linearity of sensor. Just one sensor in a lab can be a big headache for you to see whether it's linear or not. But now if you have hundreds of sensors, and calibrating it or quantifying, or I would say characterizing them could be a big issue. And how each of these nonlinearities get folded in your data analysis will be a big issue, right? Now, I mean, the sensors, the entire system, the way you run, if you are a person, many of our experiments run for about, in fact, you'll be surprised to find some of our experiments run for more than 20 years, non-stop, 24/7. I mean, it may surprise you, but these are the kind of systems or science sometimes we do. Now, imagine that the sensors that you use are, they don't reproduce the signals over a period of time, maybe connected with atmosphere conditions, sometimes aging, sometimes something else. Now, how do you take care of it, right? Now, here also I mentioned, as you put these sensors for a long time, any semiconductor material could also age like you and me. So therefore, how do you make sure the natural degradation of these sensors, their reproducibility issue, the linearity, and so on and so forth? So one of the things that normally comes to our rescue is that all the time you should know what the quality of data that you have before you can even analyze and publish the data. This is now slowly we are getting into what is the main theme of our talk, session, by saying that when you talk about very confidently reporting certain thing, your integrity, why it comes into fact is because you are actually working and trying to eliminate that all these possibilities of anything can go wrong at the device level, at the data acquisition level, or analysis level, calculations level, error analysis, all those aspects you need to really take care, and you are the only person responsible for taking care of it. You cannot say anybody else in the group are the responsible people because you are the PI of it. So therefore, your really things start right from there. So when you start using instruments, it doesn't matter the instrument is a very sophisticated one or a one that you typically use in a teaching labs, right? But all of these every one of these instruments come with certain limitations, if I want to call, or certain metrics, certain specifications, if I can say that. Okay, if I have a scale, a ruler with which I want to measure, okay, if you can't measure anything significantly better than a millimeter, right? Because the marking is roughly about a millimeter. Now, if your eyes are very good, maybe you can do half a millimeter, but not more than that. And similarly, an instrument like this, it can only give you maybe a fraction of a degree, right? And similarly, a time that you want to measure, or an angle that you want to measure, or maybe something under a microscope. Each one of them come with the standard specifications, which they say least count, dynamic range, and or what you can say, the variation with respect to aging, and when often you want to calibrate them in the labs or in the test facility and so on. So you must understand thoroughly what are the instruments that you are using and what are the limitations or specifications, characterizations of each of these instruments. Without that, all your errors are going to get accumulated, and that is how even unknowingly your results are going to be dishonest. Okay, so therefore it is most important, because when you measure certain thing, the kind of error that comes in sometimes may be an absolute error, because the true value that you want to measure is what is what, but you used a wrong instrument and measured certain value. So therefore, obviously, the difference between them is absolute error, the error that I actually did during the measurement itself, right? Sometimes I can talk about, okay, I can give it as a relative error because this is my absolute error. Out of that, I expect the true value to be so and so. It's a matter of how you express it. I can also express it in terms of percentage error. But that's not the point. The point is that if I use an instrument which is not suitable for my experiment, right? Even one instrument, and that is the big source of the errors that are going to creep in. Every time we talk about setting up an experiment, two main parameters that come to our mind, which, as I said, many times you don't even realize what kind of errors are creeping into your data without you knowing, and you go ahead and publish them. One is, of course, accuracy, how accurate your data is, and how precise this data is, right? If I think about a value that I want to measure, let us say I want to measure the acceleration due to gravity or gravitational constant, or I want to measure Young's modulus, or whatever it is, right? That is, I know that there is a reference value here. If my value comes right bang on this number, I can tell you that my accuracy is absolutely infinity, which means that I'm actually reading what I'm supposed to read. That means my instrument is absolutely doing a great job. Okay, but most of the case, you always have certain bias in measurement. Maybe the instrument has a zero error or whatever it is. You end up actually measuring the value which is far from the reference value, okay, which you call accuracy, is a DC value. Why I say DC? Because it is displaced from the actual value by certain value, certain number. right? But no, it is something like saying that, okay, so my kind of accuracy is a little bit low. I wanted shoot obviously at the center of this, but I ended up shooting at this point of time. That is fine, not an issue. But what about the other one? Other one is if I take n number of measurements, is my each subsequent measurement coming right on the top of the so-called reference value or shifted reference value? No, there seemed to be a distribution around it. There is a each measurement that I'm taking is actually coming close to the accurate value, but there is a certain distribution, which many times we call it as the Bell distribution or Gaussian distribution, which has a finite width. It is not like a delta function, which is actually sitting on the mean value or the value that you have. So this is precision. Precision means given the fact how much I'm actually moving out of the reference value or accurate value. So, for example, this value, if you look at it, it is very precise because all values are close by. Obviously, it is not so accurate because it is far away from the expected value. This is the other way around, where I have quite a precise, quite accurate value, but unfortunately, the numbers are scattered all around. So, therefore, it is less precise. Okay. So, as I said, especially when you do measurements in space or defense or science, or I mean, this is generally true everywhere, but both these numbers having a very, very eagle eye kind of a thing on these numbers becomes very important because the errors creep in without you noticing what happens in your data. So therefore, if you are an experimentalist and if you are set up a simple or big experiment, you must be very, very thorough and an expert on estimating, firstly, locating all the types of errors as well as estimating each one of them, either by calculation or by measurement. You can actually start by saying that, okay, there are some errors which are absolutely gross, which is because I did a very sloppy job of actually doing a measurement. It could be a kind of systematic errors, like the way I said about the accuracy shifting, because I used an instrument maybe which is not accurate. I used a scale where I am supposed to measure better than a millimeter. So therefore, there is an intrinsic systematic error. The random errors is what is contributing to roughly the width of the distribution, which is more like what we said precision. The instrument error itself, in the systematic error, is a combination of the instrument error itself. As you said, it is not meant to measure what you measured. Maybe it has an intrinsic offset, intrinsic zero offset error or non-linearity or whatever it is. Sometimes the same good instrument over a period of time, depending on at a higher temperature, higher pressure, or maybe humidity, whatever, depending on what is the principle of this instrument, the environmental parameters can also influence the instrument. And of course, ultimately, if I do wrong observation error, simple parallax reading errors or something of that sort, all that comes down to systematic error. So all these three main errors and then the systematic errors are also further divided. I must have a very, very thorough knowledge. Let me tell you, a person who knows the best sources of errors in an instrument or experiment would be the most successful experimentalist, in my opinion, right? So just to give you somewhat schematically speaking, so this is the value that I want to really, this is the value really I want to measure, which is at the center of this quadrant, the true value what I want to measure. And as I said, the arithmetic mean, depending on the instrument errors, I can actually take it off a little bit, but you can see that it is sitting just shifted by certain value. And these are all the values which are single measurement, each measurement, which is causing problems with my precision. So on the other hand, if I do systematic errors only, not random errors like this, then as we already said, that the whole average value shifted to somewhere else, but it is still sitting very neatly like a cluster. But as long as I know what is the distance between these two, then I can always correct it. That's why sometimes I say it's a DC value. Okay, so I think we already kind of talked about a little bit about this, so maybe we can skip this easily. But the main important thing is all the systematic errors actually are uncertainties which are due to the data that you have in the bias. Okay, it is nothing to do with any of the statistics per se. But even if I have the best instrument which is measuring very well, but I can also have random errors which are mainly caused in a big experiment by statistics. To very quickly give one example on this page, so even if I want to measure a voltage at some point and take a multimeter, depending on what multimeter that I use, whether or not it has some offsets and so on, is what is constituting the systematic errors or the way I'm measuring it, etc. But if I only take 4 measurements or 10 measurements of the same value versus, let us say, I take 1,000 measurements, right? Statistically, the second set of experiments are very significant. So therefore, I can expect the error bars to come down very, very significantly. Or for example, the sample size, if I were a person who is going and predicting which party is going to win elections, right? I mean, depending on what is the sample size that I have. So therefore, it is systematic error. The way I'm doing the polling, biased, maybe I'm not doing uniformly everywhere. That are all biased to systematic error, but the sample size will decide what is the accuracy of my measurement. Okay, so the total value that I'm talking about here, honestly, what I want to report to the in a paper is the central value, and which is again a quadratic sum of the random error plus systematic error. So I need to kind of very, very accurately estimate both of these, and this is my actual measure value. These are my, so within these error bars, I am not confident that the value is T or T plus ER or minus ES or whatever it is. So as I mentioned to you, so once again, so if it is only distribution with a random error, I'm not, the random error is not going to kind of affect the average. Average is sitting here, only it has become broader or narrower. On the other hand, systematic error moved the whole thing away, okay, but then the accuracy remains, the precision remains the same. So I need to kind of distinguish both these and estimate both of these values, right? Some of us, I mean, maybe don't bother to, don't get scared with these kind of view graphs. But my point I wanted to tell you, suppose if there is a situation where your expected value happened to be 1, okay, you can see that it is sitting right here. Now, these were all measured by different agencies, different channels, you can say, let us say, okay. Now, what happens is, now you can see the way the for a publication, the way you must really represent the whole thing is that this is my central value and this is the total error, and you can see something is written plus or minus. Okay, now this could be plus 0.09 or minus 0.09, right? And you could also see sometimes the minus and plus are not the same. So that means the errors are going to behave differently on the positive side and compared to negative side. We normally say we happily write plus or minus, right? It is not necessarily plus and minus act the same, because your instrument may behave in a plus voltage when you measure, it might behave differently when you measure negative voltage, for example, okay? Now, as I said before, this error is in some sense quadratic sum of statistical error and systematic error. And you can see again, each one of them are plus and minus are independently calculated and computed. And then, the final value is put up here. So it's a serious game. I mean, publishing papers, publishing results from an experiment is a serious game. If you are not careful, you can land yourself in trouble, because you may be reporting something which is in some way a dishonest data, even though you are actually not meaning to do that, but because you didn't estimate it properly. Another big problem, again, it's a very thick slide, so I don't want you to read it, but I just want to say a few words about this. Many of us, not necessarily students, but many of us, even researchers, academicians, we face one problem about what is the most significant digit of the data that I should report it, final reporting, when I write a paper. I'm not talking about when I do analysis. By analysis, I can put any number of digits. But if I have a number which I computed to be like this, and if I know because of the previous slides, my error is going to be of this nature. Now there is no point in actually giving infinite number of least significant digits, isn't it? I must know this data is relevant or significant up to how many digits, and that is given by the error here. So therefore, I should not report a number which is more than more than in the sense better than the error bar. Now I just want to take you back. You look at these numbers here. Okay, the numbers are all given up to the second decimal, right? Why? Because you can really see I have errors which are of that nature. I cannot say it is 1.571. This is absolutely will be wrong, and the paper would be rejected. They won't even read your paper because you don't even know that the error bars are larger than the significant digits that you have put in. And this is, as I said, it is no disrespect to anybody. All of us make these mistakes, and every time a graduate student make a presentation, you will find that they talk about numbers which go into infinite number of decimal places with no significance at all. So therefore, we must be very, very careful. It's not only about honesty, but it is also about what you are sharing with others. For example, sometimes we also do rounding. If I want to do rounding of 2.346, what do? We say 6 becomes more than 5, so we put 2.35, and then this 5 will again bring it to 2.4. We say, if I want to put one significant digit, we say 2.4. It's not correct. It is actually 2.35 if I want to do 2 digits, and it is, if it is 1 digit, then I have to talk about 2.3. Okay, so one must remember these. This is the language that the experimentalists understand. So we also must remember this is how we need to be kind of honest when we report our results. Okay, now many times we take data. For example, even if you do a simple experiment in a teaching lab, okay, we ask the student to go and do a Ohm's law, for example. We say that, okay, keep changing the voltage and measure the current, and I want to see what is the resistance that you have. I know it is a stupid example, but I'm saying that it's a simple experiment. Okay, we know, I mean, the student obviously knows that the relation is essentially a linear. It's a straight line equation. And then what you tell them is, you say you take these numbers at a lot of voltage points. Why? I mean, in principle, if I want to only measure the resistance, one value should be enough, right? But due to the reasons that we talked about in the previous slides, you tell the students that you take, large number of samples, 10, 15, 20, whatever number of samples, and then plot all these in one graph sheet and show me that fit these lines, fit these points, obviously in a straight line. The student is supposed to know what kind of fit to do. In this case, it is straight line. In some case, maybe parabolic. In some case, maybe an exponential. In some cases, it is maybe something to the power of polynomial. X power n, for example. Unless you know what physics you are talking about, unless you know what the parameter is supposed to behave, you cannot fit blindly. Oh, the points seem to be linear. No, how do you know? I mean, they may be looking, actually it's supposed to be exponential, but you did a bad experiment because of which the points are coming to be a linear. So you should not just look at the points and decide what should be the correct fit. You should know the basic physics that is happening, which is causing this particular data coming out. So then you go ahead and fit that according to that. You can see that there are large number of samples. Each sample has its own error bars, both on the X side as well as Y side. I'm sure all of you are familiar. When I have one data point which I want to mark in the graph sheet, I'm going to mark that data point at the center. That's okay. But I'm also going to draw, you can see these bars on the horizontal and vertical. That indicates what is the error on each of these measurements. You might say, if I do an experiment, the error should be same. No, like that. No, it is not. The multimeter that you use maybe has a different error at a lower voltage. Maybe when you go for higher voltages, maybe the error bars are different, right? So therefore, you have X and Y direction, the errors marked individually. Now imagine, for some reason, the great physics that one talks about here has a certain hump on top of a background that you beautifully see here. So one should be able to identify this very well, provided that you have found out what is the right fit for it. Okay, right? And incidentally, I can tell you this particular graph is a Nobel Prize winning plot, right? So now why did I kind of share that? If you do a kind of slightly sloppy kind of fitting, it is possible that this sum is kind of disappeared somewhere and you happily fit an exponential and forget about this particular signal. This is what I said some time back. Something not fitting your hypothesis could be a window to a new science, maybe a new physics that nobody had actually seen it before. So you have to be very, very careful about it. Now, coming to the point, how do I know what is the quality of the fit? How do you say this fit is fine? This is the best fit for it. So there are various parameters. Like for example, when you do an Excel and ask it to fit, it will give you a value like regression and so on. These are metrics to say the quality of the fit. We normally use what is called chi-square. Maybe some of you also use it. And by this so-called number of degrees of freedom. Number of degrees of freedom tells you that how many variables you are actually measuring. The system has how many variables. That -1 would be the number of degrees of freedom, because each of these variables is expected to vary randomly in principle in the physical space. Okay, so now if I take that ratio, normally the ratio should be something of the order of close to 1. Okay, then that is the best fit that you can expect. Tomorrow, if someone else come and trying to fit this, suppose his or her chi-square by NDF, let us say, comes to 100 by 40 or 100 by 20 or something like that, then obviously there is your fit is much better. This is one indication. There's one matrix to say that your fit is better. Of course, chi-square is essentially given by all the observed values that you have in an experiment and what is expected. This is what I told you. I mean, before you even fit, you should know what is the expected values of this due to the physics that is going in, or the science that is going in, or the engineering that is going in. Of course, you have to really do it. This is over what we said some time back. The entire integration takes place of the entire such space, and you do square. The errors could be on either way. So that's why it becomes chi-square rather than chi. And when you integrate over the entire search space, you get a value which is of the comparable to the number of variables or number of degrees of freedom that you have. So no, it doesn't matter whether you use chi-square or use some other attribute. That's not the point. The point I wanted to say is that it's not just looking at the way of, even forget about this complicated kind of stuff. Even if you were to kind of take points which are sitting on a linear scale, maybe when you look at by your eye, you say, okay, all the points are on the line. But how do you know that they're the best straight line that you had by least square fitting, right? That is what we use, no? So therefore, we don't go by just what is visible or what you're seeing it, but you actually measure quantitatively, and that is what tells you your data is accurate. So therefore, I think one must remember the maths, the way it plays the big role. That is the only place. I mean, this is a quote by someone, I really like it. So that is the math is only the place where the truth and beauty mean the same thing. Normally, when it is beautiful, it may not be truth. When it is when it is beautiful, it may not be truth, and vice versa, right? But when you calculate something very accurately, it is very beautiful. Also, it is also means that you are actually reporting the real truth to your peers. That is how, if you look at in history of science, for example, this was the 2020 Nobel Prize was given to these three people for discovery of black hole formation, which is a major discovery in the history of science. But if you look at this person, is a very popular, of course, many of you must have read a lot of his books, very popular author, but he's actually not a physicist. He's actually a mathematician. I mean, they call it mathematical physicist, but he's the one who provided the real, what you can say, the real framework of this entire discovery. So math play a huge role when you really talk about major outstanding discoveries that come in. And even some of us, including myself, was involved in a discovery called Higgs boson in 2012, which of course this gentleman got the Nobel Prize very next year. it actually very clearly, the Nobel citation, of course, said that it is for their theoretical discovery of mechanism which is so-called the Higgs boson, which is responsible for giving mass to particles. But what it has clearly said is about our effort. It actually said that which recently was confirmed through discovery of the predicted fundamental particle by Atlas and CMS. I belong to the CMS experiment at CERN, right? What does it? What did it indicate? It actually very clearly honored that it is not just a hypothesis that alone leads you to the science discovery. It is actually a very accurate discovery, means accurate measurement, and passing through all that what I told you, from sensor devices to all the way coming up to error estimation, which actually makes the discovery very on sound footing, and that is what gives a Nobel Prize to somebody, right? So this is all based on the trust that you actually did a great job. And the same thing happened a couple of years later. This is something what is called LIGO, gravitational physics detector, which gravitational waves were sort of predicted by Einstein in 1905, but it took almost 110 years for it to get a Nobel Prize, because the measurements that you need to do, I'm not going to go into this picture here because that is not the main theme of today's talk. But I wanted to kind of say the measurements that were involved to do a discovery called gravitational waves measures something 1 out of 10 power 21 parts. So I have 10 power 21 parts and I'm measuring 1 out of it, right? So, or in other words, it is like saying that I'm actually measuring something of 1 by 10,000 part of a proton. Proton itself is 10 power minus 15 meters. Now, why these numbers, mind-numbing numbers I'm telling you, is because when you do an experiment at that kind of a scale, now you can imagine what kind of rigor, mathematical rigor, instrumentation rigor, error propagation, error calculations, all that you will be able to, you need to be able to make a discovery. And normally, when such discoveries are done by measurements, and when you want to report them, you don't report just one event or 10 events coming from an experiment, but you actually report simultaneously from many such experiments, because then only you are 100% sure, because it is done independently, measured independently, calculated independently, error estimated independently, but still you actually came to a same conclusion. Sometime back I showed you one plot which was centered around 1, and I showed you various values. They are coming from different experiments. And just the Higgs boson I talked to you also came from 2 independent experiments. LIGO results came from independently 2 experiments at that time, and now there are 4 of them. So this is all what makes a scientific discovery really a discovery, and something which people take it like something written on the stone. So therefore, all this honesty, what we talk about, the scientific rigor that we talk about, come into picture. So this is that I was talking about the instrument and the Nobel Prize in 2017. Okay. What happens if either by mistake or intentionally, something you didn't want to do it, but it happened, right? What I meant. Suppose you dishonestly submit a paper which is actually not based on what we described in the beginning, right? Okay. Obviously, somebody will find out, and then that will be a great, ulta face on you and your institution and the whole community. But what I'm actually going to show you in the next 2 minutes is something which is not even intended for. This is a very damn serious experiment, which is as serious as any other experiment. There are hundreds of scientists working for years together. They built this experiment, so-called, they actually send some kind of particles, you can say right now, don't bother about what they are, from a source, and these particles are supposed to go underground, through underground pipes, 780 kilometers from one country to the other country, and they build a massive detector. This is what I meant, okay, from going from one experiment to the other, from, let us say, Switzerland to Italy, where the other experiment is located, something like 731 kilometers. And they were able to measure the time with the highest accuracy that you can think of the order of, few tenths of nanoseconds. And they were able to kind of do all the measurements using a constellation of GPS and so on. And this is such a massive, massive kind of experiment. Okay. And then they actually made a discovery after almost 200 physicists from 30 institutions working for so long, and they made a discovery which actually meant to say that a particular particle called neutrino can travel faster than light. You know, from Einstein's the discoveries that he had done, nothing can travel faster than light, right, in the medium. But this is the first time after so many, 2012 or 14, this was discovered, and it was announced worldwide in a live telecast. And everybody was stunned to see that this would be the biggest discovery ever made, right? Unfortunately, even though they really did a great work and they showed every single graph, every single error, everything, all that. But later on, they discovered there was some small problem regarding an optical cable that they're supposed to plug in into a module which was not plugged in properly. Then this is how it should have been plugged in, and so on. You can actually see this was 6th December, the bad condition, and after a week they found that and they corrected it. And then they had to withdraw this paper. And you believe me, this was the biggest, one of the, if you see in the history of science discoveries, what is the worst science discovery? This is listed as one of the 10 worst discoveries. Now you can imagine these people are absolutely top ranking scientists just because of certain instrument error or whatever you call, even though it was not intended for, that can put you in a big problem. Now, so therefore, what you need to kind of do, okay, I'm just showing a slide which I'm not again going to spend time, but if you look at Shockley, Bardeen, and Breton, who are the inventors of the transistors, this is a photograph of their point contact transistor. Why I'm showing this picture to you is not to explain today how the transistor was discovered. By the way, it is 75 years of transistors invention for which these three of them got Nobel Prize. But what I want to show is this particular slide, of course, which happened in December, Christmas Eve of 1947. Look at this logbook. This is December 24th, 1947, some number of this log sheet, and people have given the entire measurements written on this. They also wrote who are the people who are there in the lab, who are witnessing this particular measurement. Okay, this is Schottky, obviously. So it is very important that all your measurements are properly logged and properly recorded. Okay, to begin with, maybe you'll use a logbook, but this is the first source where if a discovery is disputed, you have results which are, the raw data that is resulted. Of course, some of them you may not be able to do on a graph sheet, on a notebook, because you may be computing or you may be recording on a data, but you should never destroy the original data, because that sometimes it becomes important to kind of do those kind of measurements. For example, whom you see here, J.C. Bose, who was as great, and maybe some of the discovery that happened with the transistor, or for example, even the microwave discoveries, many of them should also come to him, but one doesn't know how he really followed it up with the documentation and patenting and so on and so forth. So it makes a major important aspect of you keeping a good record of what you have been kind of doing. Okay, Professor Rao. Professor Rao, can you hear me?
Yes, sir. I'm online.
Okay.
I'm listening to you.
Okay. Can I take another 5 to 10 minutes or?
Yes, sir. Yeah. No problem. Yeah.
Okay. So maybe I'll take 10 minutes in that case. I'll go
Sure.
a little fast. Okay. So now when you work on such big systems or experiments like that, many times, okay, of course, the dilemma comes whether you want to do a patent or a trade secret and etc. But okay, here we are only talking about mostly publishing these papers. Now, when you do the publishing, why do you want to publish? Because most of the time, I mean, the saying is there, right? If you don't publish, either publish or perish. So many times people won't know who do not publish their work. They think that you're not doing a good work. So only when you write down, like as I said in the previous slide, then that is the only way others will know that you have done certain work, and inform them that that belongs to that IPR, or that work actually belongs to you. And it might also open up some new problems for future research. So papers writing is very important. Of course, you also follow certain format for writing papers so that it reaches to a larger audience, because depending on whom you want to reach, see, you write a paper because you want the paper's idea should be reaching. So writing a proper abstract, proper introduction, which most of the time people read, becomes very important. And the problem, as well as the conclusions that you have arrived at, they should be very subtly, very nicely should be put in. Quite many times it happens that the people don't really read so much of your text body, but as long as you write your abstract and introduction properly, people would know if that is interesting, and then they'll go and actually read further studies. Of course, one of the main ideas of your quality of your paper or your experiment comes from a review process. Sometimes the review could be completely internal, where if you have a large collaboration or even a group of people, you would like the results independently checked by you, your own colleagues who are associated with your experiment, but not necessarily, let us say, on day to day. So it becomes very important before you submit to a journal. It's nice to put up. In fact, many of the journals these days also have web portals where you can upload your paper before you actually submit to a journal, so that people will give you nice comments about it. If there's mistakes, they will tell you. So it is nice after that when you publish, when you submit to your journal, it becomes a catwalk for you, right? So it is good to always take advantage of these online web portals where you can put your document for this one. Of course, peer review is a real process by which whatever results you have, they will not become sacred unless it is accepted by your peers. If you are a communication person, you would like to send your paper to a journal which is a communication journal, which is actually reviewed by people who are in the communication line. So those people, when they accept your paper to be of top quality, when it is published, obviously that is how you say it is a peer-reviewed journal. You say peer-reviewed journal because it has gone through certain review. That means your results are vindicated, your results are validated, your results are accepted, and that is what gives you certain impact in your thing, right? Of course, you need to be, as I said, it is very important that the data that you must record accurately. You want to check whether all your conclusions are proper, whether you should not hide any sort of weakness. Many times it's a typical plot we say, but we actually end up putting the only best plots that we have, right? But the arguments that you made must be very coherent in your paper. The claims that you made should be able to verifiable by somebody else. And whatever implications of your research should be very clearly mentioned, that this is what my research output is. And you should be very clear. If you are a thorough researcher, you should be able to also predict what is going to be the next in line for the research that it is going to be covered. I think journals or any reviewers are going to kind of judge your papers based on these metrics. So this becomes very, very important. See, obviously the journal, the reviewers have never, not part of your team. They never seen you. They never seen your experiment. They only go by the honesty that is actually visible from your paper, right? So that's why it becomes a very, very important thing. So they always ask, is the problem really good? And to what extent you have solved that problem? And what is the main intellectual nugget that you have put in? And what did you contribute significantly above what was already existing in the thing? And last but not least is, does what you actually gave as a result, does it support your hypothesis, right? So these are some of the attributes that make you kind of paper to go through. Obviously, I mean, when you talk about honesty, there are many things that people normally are expected to do. The ethics are like, suppose you write a paper and then later on you did some more work and then you turned out that there are some updates that you want to do. and you are on your own supposed to update this as an addendum to the papers that you have published. And sometimes it might happen that the paper that you published, somehow later on you found out, it is not somebody else, right? You found out that the results that you made may not be accurate. You should be the first person to withdraw the publication if that happens. So this is what is the paramount question of morality and the plagiarism in some way. And in some sense, we should really, as PIs or faculties, we should actually handhold and set a good example as a mentor to our young researchers. When I said young researchers, I'm actually mostly talking about our students. Now, I mean, I think since I expect plagiarism to be covered in much more detail, maybe by other speakers, of course, it is a wide spectrum of, if you look at from at the bottom, it could be very simple, stealing a few words from somewhere, some paper, or it could be absolutely taking somebody's word by word, figure by figure, lifting up, from somebody else's, or it could be your own papers which you published, as we are going to kind of say that you repeat and you copy your own text, your own figures. It could be self-plagiarism. But whatever it might be, whatever it is, small or big, of course, sometimes some of the journals, they give an index. They say now there are very good tools that are available at the disposal of the journals and reviewers, the plagiarism tools, by which one could say what kind of fraction of similarity of text one sees from your manuscript to the literature. Now there are even better tools, of course, as usual, AI, machine learning based tools, which are also going to compare even the images and figures. Olden days, images were not covered, obviously, because it was difficult to kind of map. Now, and believe me that I think ethics and morality in research, in some sense, is synonymous in some way about this particular plagiarism, because ultimately people want to discourage to the extent possible this particular, I think the worst attribute, and the authors are blacklisted, the institutions are blacklisted, conferences are blacklisted, and I think it is never ever a thing that we should even try to do, this kind of a thing, because it's okay if we don't publish Nobel Prize winning research work, but I think copying somebody's data is, I think, the worst ever crime in the intellectual nugget of things. Okay. So I already mentioned to you, either maybe due to peer pressure or sometimes maybe because of your professional growth, maybe some ranking, ratings, there are these pressures of how many papers. Unfortunately, one of the yardstick for promotions or other thing is how many papers did you publish, etc., etc. So therefore, then, people are resorting to, either you, as I mentioned in the very beginning, people are trying to duplicate their own papers. And but just imagine, apart from the fact that you are doing harm, now many times what happens is some of the meta kind of reviews that happens, especially in the health or other sectors, is also based on an automatic search and systematic reviews, meta-analysis that happens. Now, if one sees more and more of the duplicate papers based on the same hypothesis, obviously that meta-analyzer will count them as multiple evidences, multiple papers, multiple interventions, right? And it is actually, you're doing harm not just to yourself, but also to the community, if one really can imagine. On the other hand, one could think about secondary publication, the publication where, I have, let us say, sometimes the same article I wrote in English-speaking people, but I want to write a gist of that for a Marathi-speaking magazine or scientific journal. I mean, these are okay. These are okay because you want to kind of take it to a different community altogether, right? But it is not like we publish the English paper on one journal and another journal and so on and so forth. So one must, exercise constraints about it. Many times it also happens, part of the material getting overlapped with publications. We talked about this. To some extent, it might happen if I write a paper for a conference. Maybe conference, most of the time, it is often work in progress. Like I'm doing some work, And I'm actually asking my students to write up a paper or a poster for a conference. Now, when I finish my work and when I get a concluded studies, I might want to kind of publish that as a journal paper. This is accepted. This is agreed. It's not a problem. This it's not. It's a common thing, right? And what I also said about the salami slicing, I already mentioned to you. You take small fragments of one main coherent body of research. I chop it into small pieces and I go ahead and uh, publish them. Obviously, this will distort the literature, same as this in some way by misleading readers that data presented in each of these 4 articles or 5 articles are actually coming from different sample data. But that's not the thing. It is actually the same data you published many times. Okay, so I think preserving the whatever, suppose you are a material science person and you are actually doing some experiments, so it is very important that you have to keep the samples that you made or experimental setup that you created, you keep it at least undisturbed until your paper is published, because some of the journals has this requirement that if they find that it is a top quality research, cutting edge research, and you publish something very top results, and sometimes they want to independently check your sample. They will ask you to actually give it to another research group where they will be able to check independent. This is what I said. They want to check such outstanding results by more than one experimental group. Now you cannot say no, I destroyed my sample. Now that will turn out to be a little bit dishonest in some way. So therefore you must remember the major experimental setups and samples or any such thing, algorithms. Many of the magazines, journals nowadays are asking you to submit the software code so that they can check by themselves. So this becomes an independent verification. Similarly, many of the cutting edge fields that happens in our field as well. For example, there is so-called superconductivity at room temperature. Many times it happened, it created a big unpleasant situation, because somebody claimed that they saw the superconductivity at room temperature, but then they could not prove because they did not give the samples so that somebody else can check. So then it will cause a lot of what you call disrespect to the scientific community. You have to keep, as I said, the original laboratory records, the way the inventors of transistor are kept with the date and time, sometimes even signatures of witness and so on and so forth. But remember always, if you are a PI of a laboratory, the buck stops with you, not with your junior researchers or students. You cannot say, no, this happened because my student has wrongly calculated or wrongly took measurement. Nothing works, because it is you as a PI will be answerable to all the questions related to dishonesty or whatever. Many journals are now, as I said, make it mandatory to mention also what are the contributions of individual authors. Like you are supposed to actually write all this, right? To enter name of the author and whether the person conceived the idea, collected the data, contributed data analysis, or did some performed analysis, or actually wrote paper or did something. So this becomes nowadays very important, because they want to, again, in another check for integrity and honesty. It should not happen that you wrote some authors' names without their contributions. Now, another thing may not be applicable so much for you, but applicable to many of us who use huge government funds, a lot of money for research. We need to kind of explain to public at large whenever there is a major discovery. For example, this was a discovery I was talking about, where we discovered and announced about Higgs boson. We also organize, apart from scientific meetings, a public meeting where we tell that this is how your money is being used for the scientific research. Okay, so it becomes a major important part to know that we have to do. Many times it happens, experiments like ours has thousands and thousands of authors, and if you see our papers are, when they are published, each of these paper has something like 3,500 to 4,000 authors. You can see what you have here is on this slide, on the right side are the author list, and the author list continues. You can see I really had to expand my name here to just show you I'm also one of these authors here. But you see, when you have such kind of huge list of authors, it becomes very difficult to how you decide who are the authors, who are the co-authors. By the way, this is another major part that people are worried, that you bring either some authors who have not done any work into authors list or vice versa. So authors could only be people who made major contribution to your study, major revised the intellectual output, approved the final version of the manuscript, agreed to be accountable for all the research work. All these have to be satisfied, then he or she becomes author. Okay, but otherwise, when you decide author list, when you decide co-author list, some of the contributors might have done a lot of help. Maybe your accounts people, maybe your administration people, maybe somebody, maybe they did a lot of help for you. You can acknowledge them, but it doesn't mean that their name should be just put in because you want to do a favor to that person. Of course, the criteria for authorship depends a little bit whether you are coming from an academic environment or a small research group or a big, large scientific collaboration, the way I said. Normally, for the authorship of academic, normally the student gets the first name and, followed by all others' name. But many of our, this one, we all go by alphabetical order, right? So academic community, you write your student name followed by your PI or your supervisor followed by authors. But for us, we just follow because there are so many authors. So we go by alphabetical order. Okay, so I think all these are what I shared with you are something which most of it came from my own working in my lab for last 40 plus years. But I also tried to kind of generalize a little bit that which I hope will be also applicable to you. Most of you, I guess, are working in a various academic organizations. So always remember that, whatever we write, whatever we do, whatever we publish, it can only be what we actually see is the one what we describe to the outside. And they all believe that how you described is very truth, honest, and with the highest level of integrity. So on that words, I once again want to thank Professor Rao and also the team of this particular event who gave me this opportunity to share my thoughts. Thank you.
Any question? Yes, any question from participant side?
These are all research scholars, sir. 45 people across Maharashtra.
Okay.
They're all doing PhD.
But most of them are like working faculty.
First year.
No, are they working faculties?
Yeah, they're mostly.
Okay.
Mostly working.
All right. Okay.
So since it is online, they could attend.
I know that is a good, I think idea that it is online, so there's no travel involved and so on. So it's much easier for them to.
Yeah, and they're doing duty also simultaneously. Simultaneously there.
Okay, and all the talks are only from 3 o'clock all these days.
Yeah, we kept it 3 o'clock only.
Okay. All right. Yeah.
Thank you, sir. Actually, this topic was new for us because visualizing the data mathematically is very important. That we comes to know today.
Yes.
Generally, as an engineer, we are visualizing the data and predicting according to the data.
Okay.
But we should take care about the measurement. And you explain number of things about the measurement. Actually, basically the error, precision, and accuracy. That we should take care while doing the experimentation.
That's true. So what I said is whether the experiment could be very big. For example, just give a scale to you. Some of our experiments have about 40 to 50 million detector channels. That means the data is flowing out from so many channels simultaneously. Now, I mean, of course, it's a big, what you call, challenge. But at the same time, even if you do a small experiment, tabletop experiment in your lab, it still requires to look at the data very objectively and also ensure that there are no errors creeping in into what you did measurements. And even if nothing else, even if you ask an undergraduate student who is doing the first lab experiments to understand these concepts of what is accuracy, what is precision, what are the least count, what is the dynamic range, what is the calibration, it goes in a long way because we have this tendency always, right? Any one of us, what you read, we think is accurate. If something you read from a display screen or something printed in a newspaper or something in the web page, we think that it's all, gone through the test, right? It's not like that. We should be able to kind of see what is the quality of information. I mean, talking about quality of data, but even quality of information, that itself will be a higher level of abstraction. So I think it is inculcating that sense of ensuring correctness, ensuring honesty, ensuring trust, because that is the only way that others would know that you actually did a real experiment and gone through things meticulously and arrived at the solution. That becomes very important. I agree that maybe I had some of the examples that I took maybe are slightly not something one come across on day to day, but the principles remain the same.
Yes, Abba, you want to ask some question?
Yes, sir. Uh, Thank you so much, sir. It
Thank
was
you.
really a very wonderful session. I was listening each and every words of your presentation.
Thank
I
you.
really respect your work.
Thank
I
you.
just have a small query, sir.
Yes, ma'am.
I'm Abha Tiwari, and I'm a SPIT research scholar.
Okay.
And I took admission this year only, September 2023.
Okay.
And I'm from computer science engineering domain.
Okay.
Now, just let me know how to remain, consistent, patient while doing your research work. As a research scholar in computer science domain, where technology is changing in every 3 or 4 months, then
I know.
how can you trust your own research work, sir?
Yes, see, I mean, it's not only in your domain, ma'am. I mean, this thing is happening in all the field. The field in which I work, even though it is a highest level of abstraction, that way, if you really look at, it's not so much technology, but it is more of a science, and science doesn't go change so fast. Sometimes it can take decades. But the point I wanted to say is that your concern probably is that how to do a deep research on a topic which intrinsically is going to change every let us say a few years or few months or whatever. Okay, but
Yes,
one thing you must remember, ma'am. So if you remember in the beginning what I said, when you define a problem, you are actually going to delimit the problem based on what is the available in the literature. Okay, at that point of time, now, of course, literature can become enriched as you are progressing in your thesis, right? I mean, working. Somebody, hundreds of people also may be doing, and they may be picking up and solving some problems or using some different techniques and so on and so forth. But you must remember that the problem that you define, your research variables and your methodology, your analysis tools and your results, etc., are still your own. It might happen. It might happen very miraculously. Sometimes one person like you and some person far away in the South America may be doing the same thing, but that is not considered to be anything bad or anything wrongdoing or anything like that. Imagine now you have internet, you are able to Google and immediately find out what others are doing. In the days when it is to take 15 to 20 days for sending a paper to for publication or receiving a reply from them, people were in their own places and they were doing something which is absolutely original, originating from their own mind, right? In some way it was actually I would say better situation where there was no chance of somebody copying somebody else's ideas. Everybody In a bad thing is like you and me are doing exactly the same thing. The good thing is that we are doing independently, and if both of us have arrived at the same conclusion or the same result, then actually the result is been proven much better. So please don't worry that what is going to happen during the time of my research, whether or not my research topic is going to be invaded by somebody else. That is never been the so far in the history, and it's not going to be like that. But on the other hand, keeping focus, etc., of course, is a big thing. And I know for sure that it is not easy for an academician to focus on teaching itself alone, but I know that you people have much more load these days. Besides that, putting a mind in originally thinking about a problem, working on it is a big thing, ma'am. I do understand this, but it should not. You should not get digressed from the fact that whether or not what I'm doing is a niche area or not, whether it is untouched by others, and so on and so forth. There, in the history, there were instances where for example, in 1965, my seniors had discovered something very unique, absolutely unique. The first ever recording of so-called atmospheric neutrino. Okay, it was published on August 15th, 1965. A very important date, very nice. Another group in South Africa, in the underground mine, they also discovered exactly the same thing. Okay, 1 week before we did, but their paper was published 1 or 2 weeks later than ours. Okay, but even though you might say, oh, they also discovered, then that means what you have done has no value. No, they use different technique, different experiment, different analysis, different, everything is different, but they arrived at the same thing. It so happened that we were actually time wise first to discover. They were published, and they were first to actually discover as per date. But both of us are treated as the pioneers of this particular new field, which came about right after our discovery. There is a lot of faith and lot of what to say, honor. There is, you don't have to worry about any of these research outcomes.
Okay, sir. Thank you. Sir, one more question I want to ask.
Yeah.
Right now, we are doing a literature survey, and we are reading many papers, and we are reading future scope of many papers.
Yes.
Now, correct. Now, whatever I'm thinking, even one technical word, that technical word is again going to be a subset of that universal paper that I'm reading again and again. So my thinking, my idea is within, cannot go beyond the papers which I'm reading. It is again the subset of universal paper which I'm reading. So how do I justify whether, then how do I check myself whether I'm really doing innovative work or innovative thinking? Means how to check even my own ideas, my own thinking, whether I'm going in the correct direction or whether I'm rethinking the same thing what researchers has done.
Yeah, see, one problem every scholar faces during literature survey is, I don't think you're asking this, but I'm just clarifying it, that the literature survey, when you do, it kind of goes, diverging a lot. Many times you read a paper, which is the main paper your supervisor must have told you to read, then it will have a number of references, that each of those papers will have m number of references and so on, and many times you easily get lost in the whole ocean of literature. Okay, but what is important in this aspect, in this stage particularly, that is where the supervisor comes into picture, the mentor comes into picture, is to be able to kind of, I mean, you can't obviously spend whole life just reading only papers, right? So you should be able to quickly come to think that, oh, this work is done in this direction using this particular technique. Okay, now can we apply a different technique in which we are experts on, or we solve using the same technique a different application, for example. So in either of them, you should be able to make a new problem definition out of what you have read. Obviously, you don't want to say I will do the same work using the same technique and same methodology, same experiment, same algorithm, etc. So you have to define your problem somewhat uniquely, either from the problem point of view, or from the technique point of view, or from the application point of view. Somewhere you need to find a niche kind of hypothesis, which is, I mean, it can be slightly different from in the literature. It can be far different from what is in the literature. You remember in the quadrants that I have shown, it all depends whether you want to take an incrementally small difference compared to what you have read in literature, or you want to jump and aim very high and say no, I'm going to kind of solve this problem, much bigger problem than what is reported in the literature. I mean, it depends on your bandwidth, it depends on your confidence, etc. But most of the time your supervisor should be able to say whether you are able to pick up a problem which is reasonably different than what is listed in the literature. So I think rather than uh, you know getting sort of a little bit frustrated in the process, it's good to take support from your supervisor as well as some of your co-researchers. But I do understand that it is not like a one-day job that you quickly read the literature and come down to start writing title of your research papers or the area of work. Sometimes it happened it's not uncommon that somebody starts working and then he or she discovers that no, I mean, this doesn't seem easily solvable problem, or no, it is a very simple problem. I may not be able to publish enough papers on this, which are required for my PhD. Then he or she might actually change the direction a little bit. That is also there. They change the title of the thesis, etc. I know these are all little bit worrisome for someone who has just entered into the scene, but it's not as difficult as you think on the day one.
Yes, sir. Thank you. Thank you so much, sir.
Yes.
Sir, sometime our visualization based on the data, that may our first prediction, because visualizing the data as a human being, we generally predict by visualization.
Yeah,
There are
sure.
huh. And second thing, there are few examples where like mathematically monopole, magnetic monopole exists. Means for doing some certain calculation, they are assuming that magnetic monopole is there. And also in time domain and frequency domain, also someone predict that there is inverse, means inverse exists, and that's why time domain and frequency domain is there. So these prediction are based on sometimes mathematically oriented, or sometimes physically they are visualizing the data and interpreting. So uh,
Absolutely.
is it that
Absolutely.
both way it is important, visualizing
Yeah.
the data
No. I mean,
without
it is.
understanding mathematics?
No. There are multiple ways by which problems get defined. What you told is absolutely correct, in the sense that sometimes experimentally, when an experimentalist will be able to kind of look ahead and see, uh, or rather predict that these are the kind of things that are possible. Sometimes theoreticians, while working with pen and paper, they will be able to kind of propose certain things. They say, oh, as per our understanding of what we have, we expect, like you told about magnetic monopoles, I expect magnetic monopoles to exist, etc. Now, in the case of theoretician, like what I told you, an example of Higgs boson, in case a theoretician has told you, then that is a theory, of course. There will be a mathematical rigor in which everything is put in properly. Now, unless somebody does an experiment and then prove or disprove that it exists or do not exist. By the way, since you talked about this topic for some reason, I myself built a detector in 1985 to 86 in Kolar Goldfields for a magnetic monopole experiment, and we actually found that we did not discover any during that observation period. But what I meant is, it's not that they are given up. We put what you call limits. So we say that okay, energies of this scale or velocity of this scale, magnetic monopoles do not exist. But it doesn't mean we say that magnetic monopoles never exist, and so on. So sometimes it also happens that apart from theorists, there are what are called phenomenologists. They take the data from you and then apply their models and their principles, and then able to kind of predict better than just only working as with the pen and paper, like what you call theoreticians. So there are theorists, there are phenomenologists, there are experimentalists. Sometimes experimentalists able to find what is ahead. Sometimes theorists will predict something, and sometimes phenomenologists, using the existing data, existing model, they will be able to say that, oh, I expect this to happen. Okay, so it is a combination of all the communities, and obviously, as I told you, that recognition in terms of Nobel Prize or whatever it is never given until the theory is proven decisively, right? Just for theory, nobody gets Nobel Prizes.
Yes, sir. Thank you.
Yes.
Yes, any question? Participants?
Okay. I guess no one has any questions.
Okay, thank you, sir. Thank you for sparing time.
Thank you, both of you, both you and Mr. Rao. And also, I want to thank all the audience, all the participants for patient listening. I hope it's of a little use to all of you. I want to also congratulate all of you. Hopefully, you are all engaged in research, and I wish all the best as the outcome of your research, and want to see all of you with a degree soon. And some of you who have just entered into this, as Dr. Tiwari ma'am, I think Abha Tiwari, right? So don't worry. I mean, this is all a phase that we all go through. But once you get on to the rigor of day-to-day research, it actually becomes a part of life. Of course, I know time management is very important for most of you because you are actually doing many things simultaneously. But I'm sure you will succeed. Thanks once again. Thank you very much, all of you.
Thank you, sir.
Thank you, sir. Yeah, thank you.
Thank you. Thank you. So can I log out?
Yes, yes, sir. Sure. Thank you.
Okay.
Okay. Thank you all. So see you tomorrow, 3 o'clock.
Okay, sir.
So tomorrow session is by Professor Surendra Singh Rathod. It's about handling review decisions at 3 p.m.
Okay.
Yes, sir. Thank you, sir.